So, in this challenge problem, we're going to calculate the electric field at a point P due to a half-infinite line of charge with a charge per unit length of lambda. And we're going to assume that this point P is at a distance r from that infinite line of charge and at a point that's in line with that line. So recall that the electric field due to a point charge is given by kq over r squared for the value. And what we're going to do here is really add up the infinite number of contributions of a bunch of little q's that start here at a distance r and go all the way out to infinity. What makes this problem particularly easy is that you'll notice, because this point P is in line with all these charges, the electric field due to each contribution is always pointing that way. And so as I add them up, I don't have to worry about having vectors add and worrying about components and that kind of thing. So this is a calculus-based problem, so what we want to do is think about it like this. What is the little contribution to the electric field? What is the little dE due to a little piece of charge which is at a location, which we now are going to have to indicate where. So let's just imagine we're analyzing one bit of charge that's right here. Okay, it's got a little bit of charge dq, and it's at a particular distance of x. In fact, let's set things up so that we have our coordinate system x, which does this. It's the x direction, and x starts at 0 here. Okay, so the little bit of contribution to the electric field involves k. It involves the little bit of charge at that location, dq, and it involves the distance squared. So the distance from the point P is r plus whatever distance x along the line you've gone. In other words, it's r plus x, quantity squared. And what we're going to need to do to get the total contribution to the electric field, E is going to be given by the integral over all the dq's. Okay? If you like, the intermediate step here is that the electric field is the sum over all the little delta i's, delta EI's, and each of those is equal to, it's the sum over all of these little dq's, delta q's. Okay, and in the process of doing that, in the process of making these things infinitesimally small, what you're doing actually is an integral. So this is what we need to do. We need to figure out how to integrate, how to add up all the little dq's, and the way forward is to relate dq with dx, if you like, the little incremental bit that you're going along the line here. So if you like, you're analyzing a little bit of charge dq for a little width of line dx, and the relationship between dx and dq involves lambda, the amount of charge per unit length. In other words, dq is equal to lambda dx, and that allows us to actually perform this integral. So this is equal to the integral of k lambda dx over r plus x quantity squared. Okay, this should give us the electric field. I'm not worried about the sign. In the end, we know that the electric field should be pointing that way. We're integrating from x equal to 0. We're starting here and we're going all the way out to infinity, like so. So the last step is to actually do this integral. K and lambda are constant. They get to come out front. And we're really just doing the integral of 1 over r plus x quantity squared. That integral should give us it should be a minus 1 over r plus x evaluated at infinity and 0. This is the, if you like, the antiderivative. To make sure you can take the derivative of this with respect to x, and you will find that the bottom gets squared and you end up picking up a minus sign and you get back to this. This should get evaluated to, at the upper limit it's 0, at the lower limit you're subtracting off minus the minus 1 over r, x evaluated at 0. And so this turns out to be k lambda over r, and if you like, again, the direction is pointing to the left. But in any case, this is the absolute value of the electric field at a point P, at a distance r from an infinite line of charge.